is Thomas Moon, and I'll be doing the factoring polynomial section for our group. To factor a polynomial, you take a polynomial, which is an expression with two or more algebraic terms, and break it apart into smaller terms that, when multiplied together, will give you the original equation, which is the definition of factoring. And to do this, I'll work through a couple of examples. First example, x squared plus 4x minus 32. Well, since x is squared, we know that it's a polynomial to the second degree, and there will be an x in each factor, so x parentheses x parentheses. And to find out what x is added or subtracted by, we take the factors of negative 32, 1 and 32, 2 and 16, 4 and 8, and we try and figure out which one will give us 4x when added or subtracted. 1 and 32 doesn't work, 2 and 16 doesn't work, but 4 and 8 do work. So you get x minus 4, x plus 40, x minus 4, x plus 8. If you multiply those two together, you get x squared plus 4x minus 32. So we know this is correct. The second example is very similar, except that there is a coefficient on the x squared, which can be irritating to deal with. So the best way to remove this is to factor out the coefficient, which in this case is 3. So we factor 3 out from the entire equation, and we're left with 3 x squared minus x minus 32. We break that up as we did last time, and we have 3 x parentheses x parentheses. Take the factors of 30, not 90, because we already factored out the 3, and discover that if you add an x minus 6 and x plus 5, it will give you the negative 1 in this function. And then, if you multiply 3x minus 6, x plus 5 together, you'll get 3x squared minus 3x minus 90. So that checks out. Now for this one, we can do the same thing we did last time, except there's a second exponent, or not exponent, variable. That can be a bit difficult to deal with, so we factor out a 2, which goes in everything, and a y, which every term shares. So we get 12x squared plus 17x plus 6, and then that would be very difficult to factor just through guess and check. So we could instead factor by grouping, and the way to do that would be to multiply the 12 and the 6 together to get 72, and take the factors of 72 and find out what adds up to the 17 here. 1 and 72 doesn't work, 2 and 36, 3, 24, 6 and 12, none of those work, but 8 and 9 does. So you plug in a 2y, you plug that in, and then you get 2y, 12x squared plus 8x plus 9x plus 6. And then you add parentheses, and you add parentheses to the 12x squared plus 8x and the 9x plus 6, and factor out what you can from each respectively. And that leaves you with 2y, parentheses, 4x, parentheses, 3x plus 2, plus 3, parentheses, 3x plus 2, another set of parentheses. And then you notice that 3x plus 2 is shared. We can pull that out of each, and we're left with 2y, 4x plus 3, and 3x plus 2. And if you need to check your work, you can multiply these together, and you'll end up with 24x squared y plus 34xy plus 12y. And finally, we have the factoring trinomial x cubed minus a. And for this, we'll need an equation, a minus b a minus b, a squared plus ab plus b squared. And to get a and b, we'll take the cube root of each term here. The cube root of x cubed. The cube root of x cubed is x. Cube root of 8 is 2. Then we plug that into the equation up here. A becomes x, b becomes 2, x minus 2, x squared plus 2x plus 4. And from there we discover that we can't factor x squared plus 2x plus 4 anymore. And then we're left with x minus 2, x squared plus 2x plus 4. And that's how you factor polynomials.
Lead coefficient test. The lead coefficient test is used to determine the end behavior of the graph. Take a to the nth power. If n is odd, the two ends of the graph will go in opposite directions. If you have an odd degree and the lead coefficient is positive, the graph will fall to the left and rise to the right. If you have an odd degree and the lead coefficient is negative, then the graph will rise to the left and fall to the right. If n is even, the two ends of the graphs will go in the same direction. If you have an even degree and the lead coefficient is positive, the graph will rise to both the left and right. If you have an even degree and the lead coefficient is negative, the graph will fall to both the left and right. X and y intercepts. To find the x-intercept of an equation, set the equation equal to 0. And to find the y-intercept of an equation, set x equal to 0. Example, graph the equation. First we need to find the zeros of the equation. Factor the equation and then factor again until it is completely factored out. Combine like terms so you have x plus 1 squared times x minus 1 squared. Set each of the factors equal to 0 and solve for x. We get the x-intercepts to be negative 1 and 1. The line will bounce off the x-axis, since when we solved for x, it was to an even power. Now we solve for the y-intercept. We do that by setting x equal to 0. We get the y-intercept to be 1. Next, use the lead coefficient test to determine the end behavior of the graph. Since the first term of the equation is to an even power, and the leading coefficient is positive, it will rise to both the left and right. When you graph the equation, it should look like the graph to the right. Example, graph the equation. First we need to find the zeros of the equation. Factor the equation and then factor again until it is completely factored out. Combine like terms so you have x plus 1 squared times x minus 1 squared. Set each of the factors equal to 0 and solve for x. We get the x-intercepts to be negative 1 and 1. The line will bounce off the x-axis, since when we solved for x, it was to an even power. Now we solve for the y-intercept. We do that by setting x equal to 0. We get the y-intercept to be 1. Next, use the lead coefficient test to determine the end behavior of the graph. Since the first term of the equation is to an even power, and the leading coefficient is positive, it will rise to both the left and right. When you graph the equation, it should look like the graph to the right. Example, graph the equation. First we need to find the zeros of the equation. Multiply both sides of the equation by negative 1 and factor out an x squared. Further factor out the equation and you should have x squared times x minus 2 squared. Set each factor equal to 0 and solve for x. We get the x-intercepts to be 0 and 2. Since when we solved for the x-intercepts, the x was to an even power, the line will bounce off the x-axis when it reaches the x-intercepts. Now we solve for the y-intercept. We do that by setting x equal to 0. We get that y-intercept to be 0. Using the lead coefficient test, we find the graph falls to both the left and right because the first term of the equation is to an even power and the lead coefficient is negative. When we graph the equation, the line will bounce off the x-axis when it reaches the x-intercepts. The graph should end up looking like the graph on the right.
Our second example is x minus 1 squared plus 3. This is in vertex form, so we know from h being 1 and k being 3 that the vertex is 1, 3. So now that we have the vertex, all we have to do is plug in points around it. For the first point, I plugged in 0, which in the equation gives us 0 minus 1 squared plus 3, which is negative 1 squared plus 3, which simplifies to 4. For the second point, I did negative 1, which in the equation is negative 1 minus 1 squared plus 3, which simplifies to negative 2 squared plus 3, which is 7. Lastly, I did negative 2, which in the equation is negative 2 minus 1 squared plus 3, which goes to negative 3 squared plus 3, which simplifies to 9 plus 3, which is 12. And then once you've got the points, you plug them into a graph and then reflect.
Partial fraction decomposition is a formula used to simplify rational functions that have a polynomial in the numerator and denominator. They are often used to compute antiderivatives, aka integrals, which is a pre-calculus and calculus subject. For example, if you wanted to solve you would first set it equal to which you do a over x, which is the first part of the denominator, plus b over x plus 1, which is the second part of the denominator. Then you multiply both sides by x times x plus 1. And you get then you can simplify. Then you write x equals 3, which equals a plus b, and c, which is constant, equals 2, which equals a. You do this because x is the x in the numerator, so 3x, so 3 for x, and then 2 is a constant in the numerator, so write 2. And then you have a, which is a of a times x, so you have a for x, and b times x, which is b, then the constant is a. So a equals 2, so you can do a equals 2, and you can plug it in to the first one. So 3 equals 2 plus b. 3 equals 2 plus b. b equals 1, because you subtract 2 and put it on the other side, so that's 1. Alright, so then you write it again as 2 over x for a plus 1 over x plus 1 for b, and that's your answer. Here's another example. This one was a little long, so I already did it for you. So first you have your original equation, which you're going to write as a over x plus b over x plus minus 1 plus c over x minus 1 squared plus d over x minus 1 cubed. And you're going to do this because it's x minus 1 to the third power, so you're going to gradually go to the third power. Then you're going to simplify, so you multiply both sides by x times x minus 1 cubed, and you're going to get x squared plus 1 equals a times x minus 1 cubed plus b times x minus 1 squared plus c times x minus 1 times plus d times x. You're going to simplify this, and you're going to get a times x cubed minus 3x squared plus 3x minus 1 plus b times x squared minus 2x plus 1 times x plus c times x squared minus x plus d times x, which you can write out as ax cubed minus 3ax squared plus 3ax minus a plus bx cubed minus 2bx squared plus bx plus cx squared minus cx plus d. Then you're going to write x cubed equals 0, because in your original equation you don't have an x cubed term, so it's 0, equals whatever in this part has an x cubed. So a plus b. Nothing else has an x cubed. So you go on to x squared, which there is 1 in the original equation, so you write x squared equals 1, whatever has x squared in this. So negative 3 minus 2b plus c. Then you're going to x to the first power, which there is none in the original equation, so write equals to 0 again. Whatever has x to the first power, so b plus minus c plus d. Then your constant, which is in the original equation, which is 1, so c equals 1, which equals whatever has a constant, whichever is a constant, so just negative a. Then you're going to substitute a into the original equation, since a equals -1, since you divide by -1, and then you get a equals -1, so you put it into here. You solve for b, which is which is 1, because x equals -1 plus b, which equals 1 equals b. As you see, it's -1, you put on the other side. Then you have b equals 1. So then you solve for c. So you plug in -1 for a and 1 for b. You get -3 times -1, which is 3, over here, minus 2 times 1, which is 2. 3 minus 2 is 1. You subtract 1 and put it on the other side, so you get c equals 0. Then you solve for d. So you plug in 1 for b, minus 0 for c, plus whatever d is. So you get 1 plus d. You subtract 1, put on the other side again, you get d equals -1. Then, when you have all your answers, you write it out back here. You go -1 for a over x, plus 1 over x minus 1, again from here, which b equals 1, plus 0, which, so you don't have to write that at all, because c is 0, minus 1 over x cubed for d, because d equals 1. And that's your answer. Here's another one. It was, again, kind of long, so I did it for you. This one's a little more complicated, so you're just going to start out with 3x squared minus x plus 4 all over x cubed plus 2x squared plus 6x. This can be, you can factor out the greatest common factors, which is x. So you factor out x, and you get x squared plus 2x plus 6. This can't be factored anymore unless you do a quadratic formula. So what you're going to do is you're going to do